How are you? I hope you're good. So some announcement first. So I just finalized the day for the venue for our optional and our studio class. It would be fourth and fifth. Since I think I have more hours to do, so the two classes will not be identical. So you probably have to attend both in sequence. I think that would be more useful experience, and because of already the semester is over, so I guess would be have more time for you to attend. Okay, so the BA lab is the CYT 615. Okay, and second, just to remind you, the test, right, is when and where, just 1 hour. Just make sure that you bring your student ID, your calculator, your tables. Okay, it's open book. Okay. Yeah, that's pretty much I want to announce. Yeah. Now let's get back to the hypothesis testing. After that, we will talk about last two topic will be regression and ANOVA, which are basically applying what we learned from hypothesis testing and estimation. So basically, this is the last topic that is theory. After that will be more like application. So hope you understand what's going on. So just to remind you, what we have done is hypothesis testing, which essentially the idea that you try to get from the data and try to see if the claims or our understanding, right, on the population is correct. Okay, so the idea is we have some understanding from the population. We try to see the data support such kind of claim. So it's kind of, you can see, say, we work with estimation. For estimation is we have absolutely no clue about the population, right? And then we look at the data and try to make educated guess on the population. Now we just reverse. We have some idea what's about population. We try to see the data support the claim. So it's just like slightly reverse what we are doing. Okay. And the main thing is the claim is called the null, right? The null, the claim is reject the claim if it's not support. Okay. And we have two different hypotheses, right? One is called null, one is called the alternative. Okay. By construction, null is the working hypothesis, right? It's the thing that we have already from previous estimation or the things we want to test. The alternative is the thing that we would like to keep if we reject the null. Okay. So usually they are complement, but sometimes not. But you will see today more. Okay. And what do you mean by hypothesis testing? Right? You pre-specify before you collect the sample. What are the scenario that is supporting the null? What are not? Okay. So that is the way you specify. Okay. And hypothesis testing, beside null and alternative, you can decompose it into another way. It's called simple and composite. Simple is saying that some parameter of interest equal to a particular value, and composite is more than one, right? And for class, null is always simple, alternative is always composite. And for composite, what we mean in the case, what we apply in the case is alternative hypothesis. There will be two types. One is called two-sided, one is called one-sided, right? And basically, this is all the three types we have. And when to use what, okay, depends on your decision making, right? Because what we said is when the null is rejected, right, we'll maintain the alternative. And what alternative we want depends on what kind of action we're trying to take, right? If the violation of the null in both sides, right, is serious, then we'll use the two-sided one, right? Just like your auditor, probably you would be care whether it's equal to a particular value, right? That would be the case, right? And if you are a government, right, or quality control, regulating, right, and you would be care sometimes more than or less than, right? Let's remember our example on whether own a local cup, right, to see if they want to use more older version of entertainment, right? Depends on the age of the customer, right? If less than, they will keep what they are doing, but if older than, then you will be more than, right? So that is very simple to decide, right? And as I said, if you auditor, probably you want to make sure that what has been claimed by your client, right, you are willing to attest, and that has to be accuracy, okay? So, and the null hypothesis, right, the hypothesis testing basically specify, right, what are the rejection region and the acceptance region, right? And test statistics, right, which is exactly that is defined because of the random variable, right? It's whether it falls on the acceptance region or rejection region is a random variable. So, and the critical value will be the region that you will reject, okay? And in the simplest case, you can imagine, right? I have a sample mean, right? And what I want to say is I have a claim on the population mean, right? And you would be saying if you reject the null in favor of this mu bigger than a number A is a number, right? If X bar is very large, right? Suppose your claim mean is certain number, right? This, if you recall, our example is this, right? Is 250 milliliter, right? And you will not be happy if you more than, right? If you want to say, right? If you the quality control, you don't want to put more than, right? And in that case, more than certain number, then you reject, right? And how much more? We'll talk about today, right? It's actually the same idea of very similar to the idea with what we have the confidence interval estimate, right? The CI is very similar. Less than the same, not equal to the same. So don't worry, we'll go one by one. Okay. Now, it's very important concepts of you do hypothesis testing, or in general, this is a general idea of making decision based on statistics. Okay. Or actually, this is also happening in the real world, also happening in the court as well. Is when you make decision, right? You can make two types of error, right? One is called type 1, one is called type 2. Type 1 is the idea that the null is actually true, but you reject it, right? You can imagine the null is actually true, right? Say it's a bell curve, right? If this is true, right, it's mainly surrounding here, all right? But the problem would be, okay, because you're making decision, right? And regardless of what you do, you need to specify what the region that this is supporting this hypothesis, right? Most likely, if you use a two-sided test, right, you'll be saying that, okay, that will be the region, right, within which we will say the hypothesis support, right? That's an acceptance region, right? And if what we found is too much different from 250, right, then probably you would reject, right? But remember, even though this is true, right, even this actually the machine is actually correct, right? And because of randomness, we can end up in extreme value, right? Happen to be, right? Just like you're very smart, right? Very smart, you may not necessarily score 100 marks for exam, right? You may have made some mistake, make to 99, right? And that would happen, right? And that happens even though you're smart, right? You take the IQ test, can also be below certain value, above certain value, right? So in that case, if that case is true, happen to be extreme value, we make a mistake, then it's called type 1 error. Okay, and we usually denote the probability of making a type 1 error is called alpha. Okay, later you will see the classical way to do hypothesis testing is to direct control the alpha, and this is exactly what you learn, very similar to the interval estimate. Alpha is like 10%, 5%, and 1%. So that's why usually, but usually alpha is 5%. That is the standard. So usually alpha is 0.05. So that's something that probably want to keep in your mind. Okay. The second one is a little bit tricky. Okay. The second one is saying about the null is wrong, but you can't reject it. Okay. And this one, that's mean if you talk about the court, right? It's just saying the defendant is actually guilty, right? But you can't have enough evidence to charge him. Okay. The first one will be saying that the defendant is innocent. You wrongly send him to jail. Okay. So is it clear what it means, right? Because I mean, under the UK system, right? The defendant, the null hypothesis is the defendant is innocent, right? And if he's innocent, you send him to jail, right? There's type 1 error, right? And if defendant is guilty, right? But you fail to send him to jail, you release him, then it's type 2 error. Okay. And this is the beta is a little bit tricky because in the introductory class, we have no way to talk about beta, at least for our case, right? Beta is something that we don't calculate and we don't think about that. And like anything in the world, there's trade-off of these two errors. If you increase alpha, then you will reduce beta. If you increase beta, you will reduce alpha. So there's a if you say just that means that if you pick the alpha, that's actually what you do. You pick the alpha, you pick a small alpha to higher beta. Right? The reason is very simple, right? You pick a smaller alpha, then actually make this region very small, right? The extreme region very small. But even it's not 250, right? It may be somewhere close by, right? And that means that you will less likely, right? Not to reject it, right? Because even it's wrong, right? Make it smaller, right? Then you are failed to do it. Okay, there's a trade-off. And one important thing I want to mention is terminology. Okay, alpha is called the significance level, and 1 minus beta is called the power. So these are the main important, and 1 minus alpha is called the confidence coefficient. But the main thing is the significance level and the power. And I hope you can remember these two terminology because they are probably important. Not the basically you make decision always you trade off these two. Okay. And to give you a more concrete idea, you can look at this table, right? And if the defendant is innocent, right? And you let him go, you make the right decision, right? If the defendant is guilty, right? And you send him to jail, you make the right decision, right? And there are 1 minus alpha, 1 minus beta, okay? And here we have alpha and the beta are the errors you make, right? So basically, this is the 4 different outcomes that you actually would do, right? Because of course, we want to have alpha equal to 0, beta equal to 0, right? That's the most, and that would be the best thing you want to do, right? But because we are collecting data, okay, unless we are looking at all the whole sample population, we are never able to alpha equal to 0, beta equal to 0, right? Because we are only making our judgment based on some part of the data, right? Some part of population called a sampling, right? And that is the thing. And alpha and beta trade-off, okay? And as I said, alpha, the rule of thumb is 10%, 5%, and 1%, okay? And you will now see why we have this, okay, very quickly. So before we do that, we need to define the p-value, okay? P-value tell us, just definition will be more clear later, but p-value will be just the smallest type 1 error, right? The statistical level that will reject H now, okay? So it's still a little bit tricky. We'll define formally, you understand what's going on, okay? So it's just a definition. We will revisit again quickly when we talk about the exact test, but here's a definition, okay? I will be more clear later, okay? So basically, this is just saying that because you control the alpha, right? Just you change the alpha such that this is exactly just reject, okay? We'll be more clear later, okay? So here is the in general how you do hypothesis testing, okay? This is the way to do assignment. This is the way you write the projects and so on and so forth. Every is a static point like this. You're starting to write what's a null alternative. Then based on the way you do, you do the Z, T, and F. You'll be clear later when to use the what. And then based on you decide what's the alpha, okay? You will tell me whether you reject or not reject, okay? I mean, here is a little bit not clear, a lot of things, but a good example one by one, then things become clear. So we can go back to the slide later, okay? I just put here, you will see the overview of that, okay? So now we are actually heading to tests, okay? Don't worry, you notice that the what we do today and next class is pretty repetitive. It's very similar all the time. So you will see it's not something complicated, okay? So the main thing is most of the thing in this topic, except the very last one, is focused on the sample mean, okay? Or we want to know population mean mu, right? And either you assume the underlying is normal, okay? Or you under last sample, under central limit theorem, there's the bell curve, okay? So we will have this, okay? And now we need to remind ourselves, right? When we talk convergent interval, it depends on whether we know sigma, okay? If we know sigma square, we will call it Z square, Z test. Otherwise, called T test, okay? So remember that when T have to apply, we cannot just rely on central limit theorem. We have to assume the underlying is a normal, okay? Because this is what the T dispersion is about, okay? For if you know, actually, we don't need to make the assumption of normality, right? We don't need to assume X, right, as a normal, right? So that is a thing. So let's go to the example directly, then you will see how this operate in practice, okay? So the idea is the following. Hypothesis testing is to assume our hypothesis is correct, okay? And see how likely the hypothesis is actually realized. We quantify them by probability. So the idea is following, okay? Let's see quickly how we do it, okay? So suppose the hypothesis, okay, is this one, okay? So that means that under the null, okay, the bell curve like this, right? That's what it means, right? This is a bell curve, right? And the variance is sigma square over n, right? And remember, the larger the n, the more squeezed in the bell, right? That's what we know, right? And this is X bar, right? And usually what we do is convert that into the Z, right? Convert that. This becomes 0, and this becomes the standard bell, right? And that is the thing we know, right? So we know if this is true, right? The sample means will be bell according to this, right? And later we see if the sample we got is extreme value, then it's unlikely that this is true, right? Because if this is true, it should be largely around here. Okay, so let's actually did that. So don't worry, that will be something that we'll do many times. Okay, so as we said, let's draw that again. Okay, what we have is under the null hypothesis, right? X bar is like this. Okay, and the alternative, remember, here is mu bigger than A, right? So it means that we would take an action, we worry if X bar is too large, right? In the other word, we would think, right, if somewhere here is very large, right? If far away enough, then we would be saying that we can't support the null, right? We cannot support X0 rather than X0. And how usually quantify that, right? Same as hypothesis testing, right? We will call this far away if this area is small, right? Let me repeat the statement, right? Because we want to say X bar to the A, and we are not very happy. We are not happy to keep this when X bar is too large, right? And how large is too large? And how large? The larger than this, the smaller than this guy, right? So we want this as small as possible. But how the small as possible? We will get the idea, right? And actually, this is exactly the alpha, exactly the type 1 error. Because even this is true, we can end up in here, right? So by doing hypothesis testing, we directly select the alpha, right? We select exactly what we call big enough, okay? And big enough is in terms of probability, right? Because it's a bell curve, right? So, and that means, right, the following, right? If you consider this case in a Z, right? This is CO1 again, right? And remember, for this to be alpha, let me draw this. For this to be alpha, that's very simple. This is just Z alpha. So I hope now you see why we use the Z alpha notation, because exactly fit in here. Okay. So you want to check, okay, this is Z alpha. To remind yourself, what is this? In Excel, it will be this norm. Sorry. Norm dot S dot inward, right? 1 minus alpha. Okay. That will number that you look at the table, right? And see this number. Okay. And okay, what you do is, in the actual practice, what you do is, right, you will be collecting the data, right, come up with X bar, right, minus the A, which is someone give you, and we said we know sigma, we have that, and the data sample size, you know, right, and it can be somewhere here, right? If somewhere here, then it convert to somewhere here, right, by this formula, right? And if that's the case, it's not far away enough from A, right? In that case, you don't reject. Okay, you keep our X0. Okay. In another scenario, O is far away, right? And actually it's here, right? The same, right? So in that case, you reject H0 in favor of H1, right? And that's why this is the value whether you make or break, right? That's why this is called critical value. If the value is so critical, it would change your decision from rejecting or not reject, right? Whenever beyond this Z alpha, you reject, right? Now, the next one is called the p-value, okay? The p-value idea is very simple, right? The idea is, suppose the blue is your data, okay? Blue is your data. Now, you can change the alpha, right? Such that this is just reject, right? You can change the alpha, move around the alpha. In the case that this is just the critical value is exactly the data you have, right? And that means that we call this guy here, right? How big is this area? It's called the p-value. Okay, this area, okay, that's the p-value. Okay, and why we want to do that? Because you can compare the p-value to the alpha, right? And if the p-value is larger than alpha, you don't reject. If p-value less than alpha, you reject. Okay, so don't worry. We'll go immediately to actual example, then you will know how to do. So don't worry. It's just very mechanical. We'll do many examples, then you know. It's just like calculus, right? The process can be complicated, but you do a lot, then it will build into your body. It's very simple. So don't worry. We will do enough example that there's no way you don't understand. Okay? Okay. So don't worry about it. Let's do example, then you will see. Because basically, when the first time you learn it, it's very overwhelming. Okay, I can understand that. Even I first learned it, it's not easy. But you will see once we do enough, then you will understand what's going on. So don't worry, we'll do one by one. Okay, let's actually do this question, and I hope that after that, then you should not have issue. So the question here is, I have a normal, right? It's 4, right? So now underline is normal, that's fine. And I have a random sample with sample size 64, right? So just to remind yourself, before we do it, right, what we do is X bar here, okay? And we have mu is 6, right? So what we claim, or someone claimed is 6 here, right? That's a bell curve, okay, somewhere here, right? And the variance is sigma square over n, right? So that would be how the bell looks like, right? Remind yourself n is 64 here, right? And sigma is 4 here, okay? So this thing I know, okay? I know how to spread this graph looks like, okay? So what I'm doing is x1 is more than 6, okay? More than 6, I will not be happy, okay? So that's the thing. Now, I collect the data which said 7, okay? So before we do that thing about this, if x bar is 5, okay, what will you do? Actually, don't need to do anything. X bar is 5, you can go home. Why? Because you will not be happy if more than 6, right? If this is 5, then bye-bye, go home, no need to do anything, right? So only if more than 6, right, you will try to do something, right? You want to see whether is it bigger than 6 enough or not. Is that clear? Because you will not be happy more than 6, right? Just like imagine you are the quality control, right? You don't want to be more than 250, right? Because more than 250 a lot, then you will explode, right? Suppose the safety control, right? And if you get this is 240, then you don't need to worry, right? 249 is not, right? 250 is also okay. But 251, then you have to worry a little bit, right? That's the idea, okay? So now the question is, now it's 7 is here, okay? The question is, do we think it's further enough? Is it far away enough? Is 6 to 7 the difference of 1? Do we think it's big enough? Okay. The question again is, what is big enough? And the main idea we have is we always specify how large is this in terms of the probability on the right here, right? If the probability is very small, it's very unlikely, then it's far away, right? Because we are making judgment based on probability, right? So not absolute distance, but rather the probability percent, right? How far it is depends on how small the probability there and beyond, right? That's a red area. It's red, small or big, right? And the criteria we do is whether compared it to our 5%, our alpha, usually, right? We compare it to the alpha. Okay? Is it 5% or not? So that's a question. Okay? So let me repeat the statement because it's very important, because you will see today we basically do this, okay, throughout the class. So rather boring, but that's what we do today. Basically, just understand this logic. Okay. So the idea is whether this red area is smaller than alpha, okay, or smaller than equal to, right? It's smaller than alpha, or maybe I use smaller than, right? It's strictly less than alpha. If less than, then reject, right? So that is the idea. So how can we know this is less than alpha or not, right? And the simplest thing we do is to convert it to Z, right? We can convert, right? Always you just minus the mu, right, over this variance, right, which is sigma over root n, right? That's the case. That's how you convert it. And once you convert it, right, we know this 6, it actually becomes 0. And if we want this alpha, right, and this is just Z alpha, right, Z alpha. Okay. I want 5% here. Okay. Now, let's actually check, right? Just to remind you what is changing from X bar to Z, right? It's asking you, in this case, what is the difference between this, right? How much 7 is above the mean and measured by the standard deviation, right? That's what the Z means, right? How much standard deviation of 7 from 6, right? So that's why the absolute distance 1, right? And this is the standard deviation, right, of this bell, right? Remember, the bell will be narrower when you have bigger n, right? So that's why it depends on the original sigma, how spread is original x, right? And how much sample you have, right? And you know that actually this is 2 away from that, right? So the idea is, let me clean this up first. Okay. So the idea is what we have is use the red color, okay, to be. So when you convert that to here, right, 7 is actually 2, right? It's 2 standard deviation from the mean. Okay. Now the question is, if I use 5%, right, whether you reject, right, the Z alpha, and you can check if I want this to be 5%, I'll set alpha, okay, set alpha. I want alpha is 1.46, 1.64, okay, and this means, right, this is a critical value. I'm larger than that, right? It's very unlikely would happen, right? So that means that I reject the X now, and I take X1, okay? And how to calculate p-value, right? P-value will be just this p-value, right? It's just looking at the area on the other side of 2, right? So how do we do that? You calculate area on the left, right? So we just normal, standard, this, right? And then you put 2, right? And then false, true, right? And then 1 minus, right? Because this is the left-hand side, right? 1 minus is the right-hand side, okay? This is a p-value. And p-value is less than 5%, so reject, okay? So this is the procedure. Is that okay? So you can see it's not complicated, right? Of course, there are a lot of logic goes on, but we repeat the same type of logic again and again and again, so you will be understand. So I would say if you understand, it's pretty boring this class because we're repeating the same thing again, 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 okay? From different angle. So to make sure that you fully understand what's going on. Is that okay? Okay, don't worry. I'm doing this again, okay? This time, next time I will do the left-hand side, okay? After that, we have a break, okay? Let's do right-hand side, left-hand side again, okay? The only thing is I will change this to left-hand side, okay? So we will do that again. This is a graph, okay? Now the difference here is I'm thinking that I will not be happy if this is less than, okay? So you can see the overreaching I just saying, right? Again, assume this is true, right? This is what you have, right? It's always A is here, right? It's very boring. We know this, the shape depends on original, how variation it is, right? Depend on how large the sample is, right? So this is what we know, right? The bigger n, then the more squeeze is the bell curve, okay? Now the question again is whether the evidence is supporting X null or X1, right? And we will be saying that, okay, we will be saying that if this is too small, right? Too small compared to this, then we will not be very happy, right? This is the critical value, right? The rejection region, right? Is the area we have defined this to be alpha, right? If it's so small, then it's far away, right? So that's the overreaching idea. And the meaning of this is I convert it to Z, right? This is 0, okay? And the same type of idea, I have alpha. What's the critical value? It's negative Z alpha, right? Because 0 is here, right? It's symmetric, so it's negative Z alpha, right? As long as your value is below this critical value, then you reject. Above, you do not. Okay, is that clear? So don't worry. A good example, then you see the same logic. Okay, just you twist your head left to right, right to left, right? So there's nothing new here. As I said, if you understand, it's rather boring. If you don't understand, you take a time, so don't worry. But we'll progress slowly because it's the most important thing to understand the logic behind. So I keep repeating the logic because the math is very trivial, right? Just put in the number there. So basically, same question, but I just change the number from 7 to 5. Okay? So let me draw that again. What we know about this is under this now, okay? Under this, 6 is here, right? It's a bell curve. Okay. And how big is the bell? Depend on sigma square over n, right? Depend on sample size, right? And we know sigma is 4, right? We know that. And n is 64. Okay. So this is what we know from the question. Now we will try to see if this is true, and we are not happy if this happened, right? So in the case that 5, then we need to check, right? If X bar is 7, then what you do? Go home, right? You're done, right? Because you say less than 6, we do something. If 7, 8, or 9, then you go home, right? Just like the court, right? If you say you try to say the defendant is guilty of murder, okay? And the murder happened in Hong Kong, right? And if that guy is in Taiwan or in Japan or in US at that time, then nothing happened, right? So that's what happened. Now, there's a curious thing, now it's 5, okay? The question is, now it's 5 is here. It is 1 below 6, right? And the question is it far enough, right? So in the way we do is far enough, we look at this question is this area small enough, right? If this area small enough, then it's far enough because very unlikely, right? That's how we translate this, right? If it's far enough, it's asking in probability sense is whether probability is small enough. Okay, so we want to see this in the criteria we usually do is 5%, right? Sometimes it's 10%, 1%, but by default it's 5%, right? Because I guess every of us has 5 fingers, right? So that's 5%. Okay. And how do we do that? And we do is by transforming this to the Z space, right? How we transform, right? You remember, right? You just minus the mean, right? And over the square root of the variance, right? And 6 becomes 0. Okay. And what's 5 become? How do you change this? It's 5 minus 6, right? Minus the mean over the square root of this guy, right? Square root of this guy is sigma. Sigma is 4 over root 64, right? Which is, right? So we are looking at how much standard deviation from this guy, okay? Which turned out to be -2, okay? That means that it's 2 standard deviation from the mean, right? And is the area big or small? Okay, the question you can do is the area big and small? The question, okay? Of course, you can calculate directly using the Excel function, right? If it's norm as this -2 true, okay, then you're done, right? Because that gives you the left area, right? Once you did that, this is the answer, right? And this is less than the 5%, right? It's 2%, right? So we just reject, right? Because it's very like unlikely happening, right? Only 2% happening. It happened. We can't really take it, right? So we are not happy to keep our H now. Instead, we H1. Okay. And of course, you can do the critical value method, right? Looking at where is 5%, right? And turn out is like this, is right? It's -1.64 that give us a 5%. Right? This is the alpha, right? It's 1.64. Okay. And either you say this value, right, is more extreme than the critical value, then you reject, or use the p-value. Okay. And you may ask why we have 2 different ways. The reason is the critical value method is more classical when you don't have calculator, right? You just need to remember 1.64, right? And that's how you check, right? You don't really need to do any calculator, right? Just remember that value. But every time if you do this, you need to go to the calculator, right? And now because computer is easy, so p-value is convenient, right? And that is because the calculation is the cost of calculation is cheap. So that's why I can do it. So this modern days, we often favor p-value, right? But old days we prefer this one, okay? But regardless what we do, the same, right? So you don't need, I have 2 bullet points, you just need 1, okay? Don't do both, or just 1 is enough, okay? Either do p-value or you compare the critical value, which is 1.64. Is that clear? Is that okay? Don't worry, after the break, we'll do something similar. It's called two-sided test. And then we also will do the case where you may complain here, I have the sigma square here, right? But in many cases, sigma square is not known. We have to use S square, right? The sample variance, okay? In that case, instead of Z, use a T, okay? But the logic is exactly the same, okay? So that means that we repeat ourselves many times in this class. So that's why I said you will able to see what's going on, okay? Don't worry about that. If you're still confused, you ask me during the break, okay? Or we'll do more, then you will know, okay? So don't worry about that. So let's have a break of 15 minutes, and I'll do the U reply. 偷懶咗少少咧，即係上少啲呢個 F3，咁就 Y 乘3 Y， 咁如果譬如話 P 係由零開始計，P 零即係到 Y 其實唔係3係咁佢哋一路數咯，一路咁換啊嘛。咁 Y 就係正常應該咁樣寫比較正確啲嘅。即係 Y 就代表你應該點樣落去係啊。跟住如果上面冇，即係因為其實唔需要睇，即係你個最後嗰個就係3嘅，咁你最細人嚟，即係難啲，應該我會咁寫嘅，你當代表 Y 係應該咁樣寫先方便嘅，即係話如果係咁樣跌咗嗱，即係如果而家可以，一樣，我寫落去你冇，但係我攞俾你冇寫我都唔寫得㗎，即係你唔可以翻得㗎嘛。梗係我先，即係呢個文長啊，即係我哋平時呢個特別嘅係啊，我既然講嘅經濟就要，但係你可以問，因為我見你有兩個翻傳跟住後價，哦係啊，但係呢個佢即係你真係細知道咗解釋係點解呢個審美上係咁個係咁講，即係如果呢個係解除呢個就可能暫時落實，跟住就翻嚟就睇呢個三角係咩原方係點樣，跟住呢一個就係搞晒開兩個世界，現啲係啦，我呢個就係你嘅 assignment 最多 ，assignment 佢交得翻我嘅 assignment 佢哋Okay, so have a good discussion with some of you. So let's see. So the first question is, of course, you know it's left tail, right tail, right? Because you can either, you will not be able to choose by yourself, right? Otherwise, they'll be too easy, right? You can always choose the thing that make it so easy, right? So of course, you know what is the left tail and right tail, right? Because we're asking, it's making a decision, right? You will try to see whether, right? If your you have quality control, right? It's low sugar, right? Then the H1 must be more than, right? Less than, you don't have problem, right? So it depends on what action you take. Okay. So the question, of course, you know, by default is there. So you can later you see the assignment I give, then you clearly see it's clearly given what's there. Okay. What difference between set table and T table? Well, very different. Set table is normal. Okay, that's normal. And what's the T here? T is the thing that if this is the distribution of the sample mean in the case where I don't know the sigma. So let me try to draw this. Okay. So the Z table is the following. Okay. Suppose I have a random variable follow a certain normal. Okay. X follow normal mu sigma, say, right? And Z table means the following. Z is actually means normal CO1, right? So basically mu is here, right? The idea is, let me use other color, right? Z, right? It simply means 0 is here, okay? I convert that, okay? The conversion to this is Z. Z table actually is telling us that, okay, what this value, okay, Z convert to this area. That is what the Z table is doing, okay? You give me the number on the bottom, I give the area, okay? So that is Z table is doing. Is that clear? It's a normal, okay? It's a standard normal called the Z. The next question is asking, what is a T table, right? And T table is simply the following. T table is asking the following question, okay? And if I know this normal, right, then we can also the same, right? We have done so many times. X bar is also a normal, right? With the same mu, right? But the variance is actually smaller, right? Because we know that's what we know, right? It's sigma square over n, right? Because the more the sample size, actually the narrower, right? So that's what you know, right? And if we are trying to do estimation and hypothesis testing, right? If we know sigma square, right? We can just do the same procedure. We just test the Z table. That's what we have done, right? And today later we will talk about if we don't know sigma square, we don't know. We don't know that. That is, but we can also do the same. Cut T n minus 1, okay? We still have a bell curve, okay? But not exactly the same bell. We have another bell. The bell has much fatter tail, okay? The two sides are more extreme, okay? And you also convert it, right? You just x bar minus mu, right? Will be s over root n, right? This is how you convert, right? Just to remind you how you convert, this is x minus mu over sigma, right? And of course, right, those are different. Okay. Okay. So that becomes the T. And T table is the same idea, right? I give you this, you give me this number, I give you this area. Okay. Of course, depend on what table you're looking at, right? Sometimes they just give you specific area and different end. Okay, Excel is always convenient. Okay, but anyway, that is what it is. But I will do T table again today, so don't worry about that. T table value is between 2 and 1. You have to be careful what is T table, is the inverse and the table, but T table we also always talk about is the area on the left hand side. Okay. So I hope that is clear. We'll do this again after the two-sided test. Okay. Okay, everyone know it's Friday. Okay, today's a little bit cloudy. I agree. There is a so most of you think it's okay the speed, but still a little bit slightly, maybe can be slower. Okay. Yeah, that's true, because it's a very Buddhist philosophy question. Is there's no objective fact. What you see is depend on how you see it. Okay, it's a very interesting joke. Passing the exam is usually not. I mean, for our class, pass exam is if you take it, I never see anyone fail. So should be no problem. But I cannot say for other exam. But for exam, I think it's easy to pass. But of course, whether you get A minus, B plus, B, or B minus, so on and so forth, depends on how well you do your project, right? And also how well you perform in the exam. But passing our exam should not be difficult, right? Because we're introductory class. We are not really having a very ambitious goal. Okay. So that is the idea. Okay. So now there is a thing that we do similar to after before the break, is two tails. Okay. Is you will reject on both sides. Okay. Just to remind yourself, you do this when you auditor, right? You are not sure whether the violation on both sides, right? And the violation on both sides have bad consequence, right? And the idea is the same, right? So X bar is here, we have a bell shape, mu is here, and the size of bell depend on the sigma, right? And the n, right? And here, because we don't exactly know the problem, right? So the violation on both sides will be an issue, right? So if it is too large or too small, you are not very happy, right? Because not equal to is the consequence. Okay. And here's the trick, little bit trick here. We have to make this alpha over 2 instead of alpha. Okay, remember alpha is the, even though this is true, how likely we make a mistake, right? So even it's true, it can end up in two extreme value. So that's why when we decide alpha and we don't know which side is more likely, so we equally split. Okay. Of course, you may ask, can I still do one-sided? But because you don't know where it is, you will equally assign alpha on both sides, right? Rather than unequal. So this is what you're going to do, right? And that means that if the value is fall within this green region, then you say it's too much different from A, right? The mu, right? Is that clear? A, right? So the actual thing, what we actually do, right, is again to convert this to the set, right? Which has mean 0 here, right? And the critical value, right? This critical value would be Z alpha over 2, negative Z alpha over 2. right? And if it fall in the blue region, then you reject. Okay. Is that okay? The same thing. Okay, just now two sides, you put two probability equally. Now the only tricky part is the p-value. Okay. Remember the p-value stand for would adjust our alpha such that it just reject. Okay. And you have to make sure that, okay, if suppose the data we have is here, say this our number end up in right here, right? So what's the p-value here? You have to calculate this area and times 2. Why times 2? Because the way we do is alpha is you adjust it, right? So it will be this area and this area, right? It's a two-sided, symmetric, right? Because the area should be like this, right? Symmetrical, right? So and that's the only tricky part. The p-value is multiplied by 2, right? Because definition of p-value is the exactly we just reject it. Okay. Don't worry. We'll do the example again, then you will see. Okay. So I mean, you will see this very same concept here. Okay. Now let's draw that again. We'll do. Okay. So I have normal distribution with standard deviation 4. Okay. I have a sample size x bar here, and I have under the null hypothesis. Okay. This is 6 here. Okay. And how large is the shape is this guy, just to recall again, right? And the data we have is the sample mean is just 5. Okay, and it's here. Okay. Unlike the one-sided case, we can't go home, right? If x bar is 6, we go home. Okay, because exactly the x now, right? But other than that, we can't go home. We never go home with the two sides. Okay, almost we never go home, right? We always have to do something because we have to ask our question. Okay, is it 5 is sufficient below 6, right? The answer again is to go back here, right? We ask here, this area, but we also do symmetrically 7 here as well. Why? Because before we do that, right, we actually don't know it's more than or less than, right? So it can be symmetrically more and symmetrically less, right? So the way you calculate area, you look at the both sides. So that's a slightly little bit tricky in your head, okay? So that's why we talk about one-sided before two-sided. Two-sided have to be a little bit tricky because before you do the correct data, you don't know it's more than or less than, okay? So for us, 5 is same as equivalent to 7, right? You don't know it's more than or less than, right? The difference is 1 above or 1 below, right? So this is the area. So if you do the same calculation, which I'm not going to repeat, right? You can convert to Z, right? Which is this calculation, right? 6 becomes 0. Right? And what's the 5 here? Right? What's 5? 5 go down, it's become -2, right? 7 is 2, right? It's just 1 SD, so 2 SD below, right? So the question is this area, is it big or small, right? So you can calculate this area, right? You have to calculate these two areas, right? You got both sides, right? And this area is 4%. Okay, these two areas together, right? One is 0.208, right? Multiplied by 2. still less than 5%. So we still reject. It's still far away. Okay. Or we can calculate this probability, right? Because 5%, okay, on both sides. So either side is 0.025, okay? So you get 1.96. Okay? So do note that, right? If one-sided is 1.64, right? And two-sided become larger, okay? 1.96. Okay? So that is a little bit tricky part here. And that's the main tricky part in this chapter. Okay. You have to be very careful about one-sided or two-sided. Okay. And you'll be very clear from the question. You should know it's one-sided or two-sided. Okay. Is that okay? The same procedure. Any question? Now, is there any question? So just remind you how you can find this 1.96 again. Okay, because some of you actually asked me in the break. I just do once more to show you how to find 1.96 and 1.64. I look at the random variable. Okay. How do we find 1.96 and 1.64? Okay, just go to the slide where we have the table, which is here. Okay, look at 1.96. Okay, how we get 1.96? Remember, is this Z is here. We have this area, right? Area alpha. The right hand side is 5%, right? If right hand side 5%, the left hand side is 95, right? 95%. That means 0.95, which is essentially here, right? You read from here, it's between these two numbers, right? It's 1.6 and 0, 1, 2, 3, 4, 5. So 1.645 in the middle of these two. Okay. And how you get 1.96? We just seen, right? Remember, right? You want two-sided test, right? You want 1 minus alpha here, right? That means that this is alpha over 2 and this alpha over 2, right? So alpha is 5%, right? That means that, right, from this is 0.975, right? Sorry, 0.9725, right? Because this is 0.025, right? So 0.975 is this guy. So 1.96, right? So that's how I get this number. Okay, in case you forget, but this shouldn't be, you should, since you do the assignment, you should know it, right? But don't worry, you will do the assignment later and we will do it again. Okay. Now, as we just hint, we do T here, okay? T here is the case we don't know population variance, okay? So the same idea here, except we change this to S, okay? So that's the thing, okay? The only thing is we don't know sigma, we only know the S, which is T, okay? To know that T, we use N minus 1, okay? And later you will see it's not always N minus 1, can be N minus 2, N minus something as well. But in the topic we talk about today is N minus 1 always. So don't need to worry about that. You have to worry about which to check next class. For this class, it's always N minus 1. Okay. So let's go to the example slowly. Okay. Again, we will do one tail, right hand side, left hand side, two tail. Okay, so exactly the same procedure. We do it slowly, one by one. Okay, let's look at this. Now we have less data, okay, less information. So we assume the population follow normal. Okay, that is important assumption. You have to remember when we apply our analysis, we need to assume underlying is normal. Okay, what does that say? Is assuming the machine that produced this, okay, is a normal, it's a bell there. Okay, and we never know this is true or not. We just have to think it's normal. Okay, and if it's not normal, we don't know what to do. Okay, at least for the introductory class. So that's something that we have to accept. Okay, so the question would be the following. Okay, with data of sample size n 16, x bar 5, s is 2. So now we don't have this guy. Okay, remember we know this guy. If we know, then it's simple. Okay, so the question we have is mu is 4 and mu is bigger than 4. Okay, so that's a question. Now just based on this, let's draw what we know. Okay, what we know is the following, right? Before we do the sample, okay, we know we are going to do a sample size of 16. So before we do it, we expect if this is true, this is 4 here, right? Mu is 4. Okay, and the shape of this bell curve will be sigma square over root n. Okay, okay, and if no sigma square, right, then we're done. Okay, because that's done, right? Because we know the data we got, right, it says 5 here, right? And then we can start, this is 5 here, right? We can see, is it 5 is far away from 4, right? Look at the area on the right hand side, is it small enough? Then we reject. Okay, but the question is we don't know sigma square. Okay, then our life is terrible. Okay, then what can we do? We use the student T idea, right? Actually, the good thing is, okay, although we're going to find this area, okay, but this will be same as T, okay? 0 here. Okay. I can convert this. Actually, T n minus 1, right? Because which bell you're following depend on n minus 1, okay? Which version of T, right? T have many versions, right? And the version we pick is the sample size minus 1 that particular table, because each T bell depend on the serial number, okay? And which version you pick up depend on n minus 1, okay? The larger the n, the very close to the bell, normal bell, okay? So the smaller the n, this 2n area will be much larger, okay? And then the version we pick, we don't prove it, but it has been proven the one we should pick up is n minus 1, okay, for sample mean. But this particular case, we're not going to do any proof on that, but this is the graph we're picking, okay? Then the same idea, right? We just try to see this 5 equal to what, right? The same idea is asking how the difference between 4 and 5, how many sample variants you're doing, right? How many sample variants is different? Actually, it's 2 different from this, right? So this convert to this number 2 here, okay? We just need to check, is that area bigger than alpha or smaller than alpha? Okay, if smaller than alpha, reject. Not smaller, you don't, right? Of course, I say x bar is 5 in this question. If x bar is 3, then you go home, right? Don't need to do anything, right? Now, how to find this area, right? Excel is very direct, right? Excel will tell you this is 1 minus T, this right? And 2 is the number we have, and we have n is 16. Okay, we look at 15, right? The 15th table, then true. Okay? Because there one additional thing here to be careful compared to the Z, right? Because T has many versions, okay? From 1 to infinity, okay? Many versions. Which T table to pick? You pick the right one, which is n-1 in this case, okay? Because sample is size is 16, we pick the 15th table, okay? So calculate 3%, not, then reject, because this is far away enough. Is that clear? Okay, and some of you actually asked me the T table, how we found it, right? T table actually gives you this directly. Okay, because T table, if that's okay, I move back to the T table to show you that. Okay, is how we figure out this number. Okay, I figure out this number. Let me go back to the. If that's okay. Okay, right? I go to the. I erase it and go back to this. How do you find 1.73? Of course, if you, I thought Excel to find this one first. Excel is very simple, right? Excel will be, because I want this area is 5%, right? Will be just, that means that this is 0.95, right? I will just T inverse 0.95, right? 15, right? That's it. It's okay. Because the left-hand side is 95, right? The 15th version of the T table. Okay. And just go back to the I think this one. Okay. The T table I give you. It's a two-tail. Okay. So remember when I give you the two-tail, right? But it's symmetric. Okay. What I want is this is 5%, right? And that means that if this 5%, if this also 5%, right? And the two-tail actually means 10%, right? So look at this guy. And I think it's 16, so this is how you get this number. Okay? So that's how you get a number there. Okay? Any question? But of course, in general, you will use Excel, right? But when you don't do Excel, then you have to look at this way. Okay? Or you can pick up whatever T table you want. That's also fine. Okay? This is the one that I produced, but you can use whatever T table we have. Okay? That's how you get 1.75. Okay? Now let us again look at this T again, but it's on the left tail. Okay? Almost the same question. Okay? Let me just go to example directly, because there's no point to. Okay? So again, what I have is, this is important for T to hold true. Okay? So I have a sample of N16, mu x bar is 3, s is 2. Okay? So just always easy to think about joy table first, joy graph first. Okay? Under this now, 4 is here, right? We know this is sigma square over n, right? and this determines the shape of this, how big and how small, right? Is the bell, right? The shape. And as again, we know the sigma square, then we are done, but we don't know, right? And the data we set with 3, so it's here. Okay. And we know the sigma square, we can calculate this area, then we are done. There's nothing to do anymore, right? And that's okay, right? Because what we're asking is this difference is big enough, right? It's big enough if this area is small enough, right? That's the same thing. So, but we don't know sigma. How does it do? And someone have shown us there's a very technical convenient thing is, although we don't know this sigma, okay, we don't know this guy, but this is same as you look at this Tn-1 table, another bell, okay, which is 0 here, okay, and you free, okay, you just use this conversion, right? Just the same thing, right? 3 minus 4, difference 1, and this s over root n, right? It just x bar minus mu over s over root n, right? This is the conversion, right? You learned that from your hypothesis testing. Sorry, combinatorial interval estimate, the same thing, right? And turn out that this area and this area the same, right? So that same thing, same area. So by finding this area, you are that area. Is that clear? So the calculation tells you this is -2, right? So, and the theory tells you, you check the T table. Which T table you checking? You check the 15th T table, right? Because n is 16, you just check the 15th one, right? If n is 20, check the 19th one. If n is 100, you check the 99th one. Okay, of course, if n is more than 400, then basically no different from looking at the normal, right? But if n is small, then you have to be very careful which T table to check, right? And in general, when you apply to business application, actually T and Z will be very similar because you are looking at very large sample size. But we're still have to teach this because the scenario that you can't have that number of sample size, then you have to check it this way. Okay. And how to calculate p-value here, right? -2, right? Then just T this -2, okay? This to find the area is this, right? But you tell them T has many tables to check the 15th one. Okay. And look in the area is true, right? Because it's area, okay. Okay. So that's how you look at the area, and this area is 3%, then you reject. Okay. You can't really say that it's equal to 4 because it's too small. Is that clear? Is that okay? Is that fine? So lastly, for today, I want to talk one more final one is the same thing. Just the normal, but just the difference is two-sided. Right? Just change this two-sided. Okay. I don't want to take more time. I just mention it. I'll do the calculation later. Okay. So the idea is the same, right? I have mu is 4, so I have 4 here. Okay. Again, there's a bell curve. Okay. And the question would be, if I know sigma over root n, then there's no problem, right? The question is free is here. Okay. And it's two-sided, okay? We're asking, is it how 4 is different from 3, right? And we want to know this area, right? Is area small or big, right? But because of two-sided, okay, for us, we actually don't know whether this is actually 3, actually 5, right? And the area we care is this 2 area, right? It can be either 3 or 5. For us, before we do the sampling, it's the same, right? Because we don't know to know, right? So that's the idea, okay? If this area is small enough, then we reject, right? And because we don't know sigma, we convert to t, right? I'm not going to do any calculation. This is t here, and n-1 version, right? So what we do is you convert this 4 to 0. This is to -2, and this to +2 here. And then we look at this area and this area add together. Is it more than 5% or not, right? And that is the question, okay? We will repeat doing the same thing next class, but with different setting. So we are basically very boringly repeating the same thing again, okay? So have a nice weekend. I will see you on Wednesday.